Hello and welcome back to Calculus. First, I'd like to thank all the nice people that support this channel by liking and subscribing. Now, following the previous video, today we'll be looking at the fundamentals of derivatives. So let's immediately define what a derivative is. In words, it is the rate of change of a function with respect to a variable. In most cases, that variable would simply be the x value. In other words, a derivative is simply the gradient or slope of a function at a very specific point. Now, please recall, for a linear function, in order to find its gradient or slope, all you need are two given points. Once you have the coordinates of these 2 points, the gradient, which we simply denote with the letter m, would be equal to y2 minus y1 divided by x2 minus x1. Another common notation used is delta y divided by delta x, where delta is simply the Greek letter that represents change. Or, to put it in words, it is simply rise over run. Though it is that simple with linear functions, because they are a straight line and gradient remains constant, it does not work quite as accurately with more complicated functions. Suppose a parabola, or perhaps a cubic function. You can see here that the slopes are inconsistent, or in other words, they are constantly changing. And thus, the concept of derivatives exists in order to help us evaluate the gradient at a specific point. In the case that we need a general expression for the gradient at all points on the graph, the derivative can also help us achieve just that. And this is where we are introduced to the first principles. So let's immediately visualize this. Suppose a given function f, and we want to evaluate the gradient at the input x. And thus, the corresponding output would simply be f of x. Now we take another point on the graph, and we call it x plus h. In this case, h is simply an arbitrary number added to x. Well, and logically, the corresponding output would simply be f of x plus h. Now, if we were to connect these two arbitrary points, we would simply have a straight line with two given points and their coordinates. For the gradient of a straight line, we know that we simply need to subtract the y coordinates and divide them by the subtraction of x coordinates. And you can see on the bottom here, it would simply simplify to just h. However, you can see that this isn't very accurate. It's close, but it's nowhere near the correct answer, since our goal is to evaluate the slope at the point x. So, in this case, you would ask, what would help? Perhaps decreasing the value of h. Now let's say we have a smaller h, and now our point x plus h is right here. Now you can see if we were to connect the original h with the original x with the new h plus x, our approximation becomes more accurate. However, it is still not enough, so that just means we need to keep making h smaller and smaller. And eventually h simply vanishes, or in other words, h is going to be equal to 0. Now, what do we call as an input approaches a certain value? Please recall from the last video, that would simply be the limit as h approaches 0. Thus, the formulation we have above here is correct. However, all we're missing is the limit as h approaches 0. And here, ladies and gentlemen, is what we call the first principles. From this formula, we are able to find the exact value of the gradient at a specific point, or the general expression for all gradients on the curve. Alright, so now that we have gotten the fundamentals and the theoretical out of the way, let's go ahead and take a look at a few examples. Let's say we are given a function y equals to x squared, and they ask us to find the gradient at the point -2 and 4. Then, using the first principles, we would have the limit as h approaches 0 of f of -2 plus h minus f of -2 divided by h. Now, f of -2 plus h would simply mean -2 plus h squared. And of course, f of -2 is simply -2 squared, which is positive 4. Now, if we open up the parentheses in the numerator, what we would get is 4 minus 4h plus h squared minus 4 over h. And then you can see 4 and 4 will simply cancel each other out. And then, again, in the numerator, if we factor out an h, all we would have left in the parentheses would be h minus 4. Once again, you see simplification of h over h. And finally, we're simply taking the limit as h approaches 0 of x minus 4. And the answer here is -4. And here's your answer. The gradient of the function x squared at the point -2 and 4 is simply -4. Now, using the same example, but without a given point, we can actually find a general expression for all of the gradients on the x squared graph. Once again, we are using the first principles, however, without the given point. It means x is simply there as a variable. And when we open the numerator, what we get is x squared plus 2xh plus h squared minus x squared over h. And you can see our x squares cancel out, and we can factor out an h. Once again, the upper and the lower h cancel out, and all we're doing is simply taking the limit as h approaches 0 of the function 2x plus h. And that would simply be equal to 2x. And this right here would be our derivative. We can denote it in 3 different ways. We can write y prime is equal to 2x. We can write f prime of x is equal to 2x. Or the third, most mathematical and professional way to write derivative would simply be dy dx is equal to 2x. dy simply means we are differentiating the function y, and dx means we're differentiating it with respect to the variable x. And 2x here would be the general expression for all of the slopes on the curve of x squared. That means given any point on the graph, we can simply plug in the x value of the point, and what would we get would be the gradient at that specific x value. However, calculating all of this seems complicated and extremely time-consuming. Thus, in the next video, we will introduce differentiation rules, which allow us to compute these derivatives with ease. So I hope to see you there, and have a nice day. Bye!